and I was pretty happy. We didn't do quite as well as we've done on the other quizzes. So I think the mean was 85, which I'd like the mean to be a little bit higher. So I think for a lot of people, this is ending up being your throwaway quiz. Remember, you get to chuck your worst grade. And then also for the exams too, I weight the worst exam the least. So, just recognizing that we sometimes have bad days. What did you guys think about the quiz? Seemed like we had plenty of time, so most people finished in the time that I gave. Was that content on par with what you were expecting, or I'm seeing more no? So what on there was not what you were expecting? Yeah. The anion exchange capacity. So we talked about that at the end of 2 weeks ago. So that's fair. So we'll go over all this stuff, and hopefully it makes sense. So this question here, again, you are working with your hopelessly inept lab partner who seems to always mess up the data sets. And you had a bunch of soil waters content that were measured at 10 kilopascals of pressure and 1500 kilopascals of pressure. And we know that represents, for sandy soils or soils from around here, that would be the water content at field capacity and then also at permanent wilting point. And I think most people got that the plant available water is all the water that's in between those two pressure potentials. So all you had to do was subtract 0.2 from 0.4 in this case, 0.05 from 0.25, 0.1 from 0.35, and then 0.02 to 0.05. But you really didn't, so that you needed to know that to understand what we mean by plant available water. But to ascribe these to different texture classes, you could really do that by just looking at these for the most part, or at least looking at the ceiling and the basement values. So knowing, we see a pretty big range in the amount of water that these different soils can hold against the forces of, 1500 kilopascals or 10 kilopascals. And knowing that, we have a clay, a loamy sand, a gravelly sand, and a loam. Which texture type would we assume should be able to exert the most strength against the forces of gravity or against permanent wilting point? Yeah, the clay, right? So we know that as the fineness of texture goes up, we have stronger and stronger matrix potential. So the strongest potentials here at both endpoints would be tin 1. So tin 1 should be a clay textured soil. Well, then it might help us to bookend our potentials here. So what's the worst? This one. We have very low potential in tin 4. So of the textures that were presented here, we know that sand is the largest particle size and it has the biggest pores. We also know that sand has the lowest total pore space. And in particular, a gravelly sand would have the lowest total pore space or the highest bulk density, right? So the gravelly sand would be tin 4. And then we just have to do so we have two other choices here, a loam soil and a loamy sand. So these are both relatively close to one another. So we'd have to decide which one would be which. And in this case, tin 3 has more plant available water than tin 2 does. So we would expect that to be the loam, right? The silt loam, because those textures have the most water that's actually plant available. And then by difference, then we have just our intermediate one, which is just a sand. So this question here, this is actually taken from the back of the chapter questions. So in your book, they actually wanted you to provide 4 reasons why compaction reduces the amount of water that's plant available, but I only nominated 3. So there's a whole lot of reasons here. So the big thing is compaction increases bulk density. So that means that we reduce total pore space. We sacrifice some pore sizes. So we sacrifice macropores, we create micropores. We reduce drainage. So soil's air-filled porosity goes down. We increase the matrix potential of what pores are there. So the plants have to work harder to get water. And we reduce our air-filled pore space. So the roots, so for respiration reactions of roots, they're going to have more problems. Also, by increasing the density, we reduce the physical the physical ability of roots to penetrate the soil. So there's a whole lot of reasons that you could have nominated, and I was only asking for 3. So I thought we did pretty good there. And then this question, again, I left it pretty ambiguous by design because I didn't want us to get too specific. So there's a whole lot of ways that we could have answered this. So considering the 6 domains of clay that we had been talking about, and we had talked about a couple different ways that we could describe them. So again, going along a gradient from clay mica or illite, and then slowly weathering out into the vermiculitic clays, then weathering a little bit more into the smectite or the montmorillonite. And then with continued weathering, we lose that 2-to-1 structure and become a 1-to-1 clay or kaolinite. And then with continued weathering, we become those oxides where there's very little of that clay structure remaining anymore, basically weathering into rust or hematite. So thinking about those dominant clay types, a high water holding capacity, what would be the best example of the clays that we talked about? Yeah, John. Smectite. Yeah, so any 2-to-1 clay that can expand, that would be the best answer there. So I accepted a wide range of answers. If you just said expansive 2-to-1, that's accurate. If you just said expanding clays, that's accurate. So that a wide range of answers there. And then the least then would be anything on the far right of that cartoon that we looked at. So the oxides or the 1-to-1 clays, kaolinite, those would all be acceptable answers. Long-term source of potassium, the most would be the unweathered clays, right? So at the far left of that cartoon that we talked about. So the best answer here would be something like fine mica or illite. Any of those 2-to-1 clays that, or non-expansive 2-to-1 clays would be the least weathered. But I accepted a wide range there. So as long as you got the order right here, so vermiculite is relatively unweathered as well. So if you said vermiculite, that would be better than, say, again, on the least fertile clays would be, again, at the far right. So 1-to-1 or kaolinite or oxides. So any questions about that? And again, I accepted a wide range of answers there. And then question 4 here was, again, just acknowledging that if we measure the elemental ratios of silica to aluminum, that directly represents how weathered that clay is. So higher weathering means lower ratio of silica to aluminum. And then there was this question. So what did you guys think about this? This is a real study that was conducted not too long ago, looking at a real management decision. So they went into this hardwood forest and they wanted to release the white pine. So they did a little bit of stand conversion, and then they measured the soil constituents 20 years later. And what was pretty cool about this study is this management decision had pretty big effects on the soil fertility after 2 decades. So the calcium content went down, the exchangeable calcium went down, exchangeable potassium and magnesium all declined, and then the pH went down. Or another way of saying that would be the H+ concentration went up, right? So based on this data, what should have happened to the effective cation exchange capacity? It should go down, right? And that's because if the pH went down, that means that we've protonated a lot of the exchange sites, right? So we've added a lot of H+. So that actually should have decreased our effective cation exchange capacity. Now, I just put this in here and I accepted a wide range of answers on this because, in fact, the cation exchange capacity could have not changed or it could have gone up in response to these management activities. So how could that be? Could you describe a scenario to me where, based on even these data, the cation exchange capacity actually went up in response to these treatments? Which, spoiler alert, is actually what happened. So counterintuitively, the cation exchange capacity actually went up despite the pH going down. Well, how could that be? What would cause an increase in CEC? Did they add a bunch of clay to the soil? Did this management activity releasing the white pine magically rain a bunch of 2-to-1 clay onto the soil. No, what do you,
Increase organic matter.
it increased the organic matter, which again, I keep telling you is the answer to everything. So the release of the white pine actually almost doubled the productivity of the stand. So it was a younger, more rapidly aggrading forest. And also the white pine litter is a lot different than the deciduous hardwood litter was. So we actually started to develop a deeper organic layer. And in the surface soils, the CEC actually went up. Now, that tells us that the total number of negative exchange sites increased because of the organic matter. But what's on those exchange sites? And now we know what's on those exchange sites based on these data. We know that there's protons on there because the H plus or the pH went down. We know that our base saturation percentage, what happened to our base saturation percentage? It went down, right? Because base saturation is going to be directly related to pH. So remember, base saturation, what we mean is the amount of base cations on exchange sites. And remembering that the active pool of acidity and the exchangeable pool of acidity always want to be at equilibrium with one another. So we know that if the concentration of H plus out in the soil solution is high, then we would guess that the concentration of H plus on exchange is also high, which means that the concentration of these base cations is going to be relatively low. Does that make sense? What else is likely to be on exchange sites? Because we know the pH is low. So we've increased the cation exchange capacity. We're putting the hurt on these base cations. So what's likely to be on the exchange sites? Yeah, what do you think, John? Aluminum, right? So we know that aluminum is, so these are the base cations, but we also have the acid forming cations or aluminum. So since the pH went down, the aluminum concentration on the exchange should have gone up. Now I accepted a wide range of answers here because a lot of people clued into the fact like, well, wait a minute. The effective cation exchange capacity based on these data alone should have gone down. Because I didn't provide you any organic matter data. I didn't provide you the actual empirical evidence of what happened. So based on that, if the total CEC went down, and I just asked you the total amount of exchangeable aluminum. I didn't ask you the relative amount or the aluminum saturation percentage, which was my mistake. That's what I intended to do, but I didn't ask that. So I accepted either one. If you said the concentration of exchangeable aluminum declined because total CEC declined, that's acceptable. But what I should have asked is, how did the aluminum saturation percentage change? And that should have gone up because the pH went down. Does that make sense to everybody? So I accepted a wide range because this is a complicated study. So some people actually did nominate that transforming the stand conversion to the white pine. Some people said, well, that might increase the duff layer. That might increase the O horizon thickness. And that should increase the CEC. And I was pretty impressed by that actually, because that's actually what happened. Maybe some people actually knew this paper, but what did you guys think about this question? Was this a real stumper? A little bit?
But just might be kind of threw you off, especially if you didn't know the results of the study, I guess. Not necessarily that you had to, you could have answered it kind of, but yeah.
Yeah, I agree. That's why I put it in here. I didn't make it worth any points and I accepted a wide range of answers for that reason. But I just wanted to see how you guys are thinking about these different things. And do we understand all the potential outcomes of these management decisions? So I thought this was a pretty cool paper actually. And then this question, this was just trying to get us to think again, well, what creates CEC in our soils? And a lot of people, I think one thing that I really want to clarify right up front is a lot of people said, well, if we add more ions to the soil, the cation exchange capacity is going to go up. And that's not true. And so you can add, at Chris Miller's farm, he could add all kinds of fertilizer to his lousy Laminga sands, and that's not going to increase the CEC. It doesn't increase the capacity. So adding more ions does not somehow magically create a bunch of negative exchange sites on the soil particles. But what does increase the CEC is the answer to everything, organic matter, and then clay content and clay type. So around, if it's a 1-to-1 clay, a weathered clay, or not an intermediate clay, like a 2-to-1. And then also to some extent pH. So the big one, so in declining order, the most important for our soils would be organic matter, then clay content, and then there's some small amount of pH dependency of charge. Those would be all the big things that contribute to CEC. And then here's the question that people that perhaps thought this was an unfair question. I'm sorry about that. We had talked about how different clays along that weathering continuum, how when we continue to protonate clay surfaces, they can actually pick up a net positive charge, right? And that connotes anion exchange capacity. So that's why those more weathered clays, like the 1-to-1 clays or the oxides, have anion exchange capacity. So the charged surfaces have become so protonated that they actually can exchange anions. So that I accepted a wide range of answers here. The other answer to this question, again, organic matter, right? So organic matter is also loaded with negative exchange sites because of all the functional groups that organic matter has. So those hydroxyl groups, organic acids, those all have the ability to exchange anions. But then also the highly weathered clays, that would have been a good answer. And then just low pH, we pick up some anion exchange capacity at low pH. So I accepted all of those. So any questions about that? Yeah, Kendra.
So you said the charged surfaces become so protonated that they are positive, and that's why they can accept anions?
Exactly. Yeah. So, but if in really acid environments, if we add enough protons, we can actually pick up some anion exchange capacity. Does that make sense? Any other questions? Anything that you want to go over again? Yeah. So if we continue to add more H+, we're going to pull OH, any OH that's on exchange sites is gonna get turned into water. And any aluminum that's in the exchangeable pool is going to likely be solubilized because aluminum 3+ can only occur if it's a really low pH, if there's a lot of H+. Because if we start adding hydroxyl groups, aluminum will go to ALOH1 and then ALOH2. And then by the time we have 3 hydroxyl groups with the aluminum, it actually precipitates out a solution. If we continue to add acid, any aluminum that's in the residual or bound pool is going to weather out into the exchangeable pool. And then if we continue to add acid and we can make the aluminum go out into the active pool of acidity, it's going to further increase acidity by breaking apart water through hydrolysis. Does that make sense? So if we keep adding H+, aluminum is going to go from the residual pool to the exchangeable pool, and then it can go out into the active pool and create more acidity. Does that answer your question?
Right, and then again, when the pH goes up,
Exactly. Yeah. So if the opposite, which we hope to be able to talk about today, if we add a liming agent, such as calcium carbonate or magnesium carbonate, we start adding bicarbonate to the system, and in the dissolution of bicarbonate, those OH groups glom onto the aluminum, and then we precipitate it out of solution. Does that make sense? Any other questions? So I do have a short video. So a couple of years ago, a group of students wanted to do something instead of taking the final. So they said that they would make an instructional video. They found the soil reaction part of the chat of this class really inaccessible. So they wanted to try to create an instructional video to try to explain all the things we've been talking about. So I like to play it at this point because it's a good summary of everything we've been talking about. And I think it's kind of funny. I think we could use a little bit of humor right now.
name's Mike. The American Soil Scientists of America contacted me to dig this soil pit and get samples for them so they could study soil reactivity. Come along with me and we'll figure out how to do that. Oh, look who I found. It's the American Soil Scientists of America. I got those samples that you guys wanted. Did you guys want to talk to me about soil reactivity?
Sure, Mike, we can talk to you about soil reactivity.
Okay, great. What's involved with that?
Well, there are really 5 things that you really need to know. First, definition of a colloid. Second, the types of colloids. Third, CEC or cation exchange capacity.
That sounds complicated.
4, constant charge versus pH dependent charge. And 5, buffering. So Mike, let's begin with the definition of a colloid.
Great.
Mike, colloids are small soil particles that have either positive and or negative
I don't
charges
know how to
on
get
them. They have large surface areas, and those charge sites will attract ions of the opposite charge.
Holy cow.
We're going to focus on 3 main types of colloids. The layer silicate clays, which come in 2 forms mainly, 1-to-1 and 2-to-1 clays. The 1-to-1s are more weathered than 2-to-1s. We're going to focus on the iron and aluminum oxide clays, and these are highly weathered. They can have more positive charge sites and sometimes be a positive charge overall.
And then we have humus and organic matter. That adds lots of surface area to a soil, it adds charge sites, and it helps to reduce the change of pH because of the large amount of charge sites in the organic and humus layer.
It's not hummus.
Let's take a closer look at silica clays using cookies as an example, for this being a 1-to-1
and these being a 2-to-1. And in our example, the white filling is aluminum or iron, and the black outside cookie is silica. In our 2-to-1 here, you can see they're quite easily broken apart because there is only some hydrogen bonding holding them together.
Whereas in the 1-to-1 clays, they're more weathered because there's only 1 layer of silica per 1 layer of aluminum or iron. And if you look, it's very, very sticky and makes it a lot harder to actually pull apart because of the weathering.
Getting all this, Mike?
Yeah, this is pretty interesting stuff.
Well, there's a lot more to learn, so go ahead and grab a cookie and follow us.
Sounds great.
Mike, you might get really lucky and see some colloids right in action.
This is exciting. matter with some magical stuff. I just want to pepper my soil with it.
Are you the soil scientist from NASA?
Yes, we are. But unfortunately, we're informing a student about soil colloids, so we can't really talk right now.
Maybe next time.
Next time.
What are we going to talk about now?
Let's go to the lab and we can talk about buffering.
Like my dad's car?
No, Mike, not that kind of buffering.
Okay.
Buffering is a soil's ability to resist change of pH. And we're going to show you that using these beakers as an example.
In this example, we have two different sized beakers, with the larger beaker representing more charged sites and a larger cation exchange capacity, and the smaller beaker representing less charged sites.
Or a smaller cation exchange capacity. In this example, if we add 5 drops of food coloring to the large beaker, and if we add 5 drops to the smaller beaker, you can clearly see that the larger beaker has a better resistance against the change of pH because of the lighter color, whereas in the smaller beaker is very dark blue, showing that it can't really change and resist the change of pH.
Okay, so buffering is basically the soil's ability to resist change.
Yes.
Great.
Good job, Mike.
Dignity, innovation, research, tenacity.
Oh, hey, look who I found. It's the American Soil Sciences of America.
Mike! God.
Oh, hey, Asa. How's it going?
Let's begin with the definition of a colloid.
Great.
A definition.
Good?
Yes.
So, Mike, let's begin.
Come on, you got this.
I got
Come on. This is still the beginning. We still haven't even gotten to the shit. I have to say, if we can get that part right, then we can just like edit it and maybe even talking. We just need to get this right.
Wow, that organic matter is some neat stuff.
Are you the soil scientist from NASA?
You didn't say magical stuff. You gotta say magical stuff.
See that?
You close that on campus so we can try that later?
Oh, yeah.
What was your first reaction to that?
I thought laughter. Yeah, we're gonna do interpretive dance for the final. So is that useful? Possibly. So just to review, what buffering is talking about is really talking about the ability to sacrifice some charge to negate a change in pH, right? So that buffering works in both ways, where if we add H+, we can resist a change in pH by sacrificing a negative charge site. And if we add OH-, we resist a change in pH by sacrificing a positive charge site, right? So does that make sense? That's in a simplest sense what we mean by soil buffering capacity. And that's why if we have more exchange sites, we have a bigger ability to resist a change in pH by exchanging negative charge sites or positive charge sites. Does that make sense? So just to illustrate that study that I talked about in the quiz. So this is the real data here. This is total cation exchange capacity in the centimoles of H plus. And another way of saying this would be exchangeable acidity or direct measurement of pH. So we'd expect the H plus concentration to go up if the pH goes down, right? And then the base saturation again went down as we would expect. So in this particular case, the total cation exchange capacity actually went up despite an increase in acidity because of the increased organic inputs to the soil. So that was a pretty cool thing, a pretty cool finding. So that's about all I wanted to go over with respect to the mechanisms behind soil reaction. I thought I'd like to spend a little bit of time talking about some of the management implications about why it matters. So we know that CEC is important because it directly reflects buffering capacity, but there are also some things that we can do to actually manage for cation exchange capacity. One is increasing the organic matter content. So we know that that's going to increase the CEC. And like we saw in that previous example, management decisions that affect the inputs to the soil can increase the organic matter content. So that's a pretty cool thing. And we care about this because CEC is it's our sole mechanism for holding on to nutrients. And interaction with pH determines what's actually on the exchange sites. So some of the things that we can actually manage are pH dependency of charge and the organic matter content. Again, clay content's really important, but it's a pretty hard thing for us to manage. I mean, I guess there are some mitigation things that you could do to avoid erosion, but you're not going to really add clay to the soil, right? That just wouldn't be practical. But we can affect the pH through liming, as I had mentioned, and we can affect the organic matter content through harvesting practices, and also not so commonly in forestry, but in ag systems, adding fertilizer would increase the production side of things. So liming, what we're talking about here is actually the addition of citrus fruits from, no, we're not talking about that at all. Liming is, yeah, if anything, it's the opposite of adding citrus fruits, right? So we're talking about adding these base cation rich minerals, particularly dolomite. Here's what it looks like in practice. So you can think, from an ag standpoint, there are ways to disperse lime across field, but in a forestry setting, I mean, you've all probably seen what it looks like after a harvest, especially, after a select cut. What describe it to me? What does it look like? What does a harvest look like? It looks like a war zone, right? So can you imagine trying to, in a practical way, trying to evenly disperse lime after a select cut? No, it'd be very hard to do. What we did is some experiments in northern Wisconsin where we did some clear cuts, and even clear cuts are really messy, right? There's slash everywhere, especially if it's a winter clear cut. The stumps are pretty high. So it's still a logistical headache, but we did manage to do it. And we did something like you would do an ag, but we retrofitted a skidder with a live bottom spreader. It was modified from the same kind of spreaders that are used on roads to disperse salt. So that actually worked pretty well. But it all started from, ag applications. And Annika's question was right on point, because a lot of these pH mediated reactions are similar to what happens through the dissolution of calcium carbonate when we produce hydroxyl groups, which scavenge up the protons, and that's how the lime agent works. But primarily what's where the rubber meets the road is the production of these bicarbonates. And that's what's doing the work. So the bicarbonate is a lot more soluble than the carbonate is. And because of that, we tend to scavenge up protons off of exchange sites. And the net product of this whole reaction is the production of CO2 and water. So in effect, to quantify the amount of lime that you would need, You would do just like what we did last week. You'd have to know what your total acid saturation percentage is. And then you could calculate the centimoles of charge associated with the calcium to calculate how much lime you would have to add to counteract that exchangeable acidity. And then according to your textbook, you do all that careful math, and then you have a fudge factor of 1.2 or something to account for things like the grain size of the lime and the pH of the soil, the active pH of the soil. So you want to make sure that the reaction thoroughly goes from the left to the right. So just to kind of illustrate this, very similar to what those students did in the atrium with the pieces of paper representing the ions associated with charged surface of a soil particle. If we were to add our calcium carbonate, and again, the dissolution of the bicarbonate produces these hydroxyl groups. And you can see what these hydroxyl groups are going to want to do with the aluminum, right? If we add enough, if we continue to weather and continue to push this reaction from the left to the right. And I should mention here that this reaction efficiently wants to go from the left to the right because the soils are super saturated in CO2. So there's a lot of CO2 in the soil environment that's going to be really effective at pushing this to the right. Does that make sense? And then furthermore, in the dissolution of bicarbonate, we even produce more CO2, which goes to feed back and further speed this reaction. So that's why lime doesn't persist in the soil for very long. So in producing those hydroxyl groups, we produce carbon dioxide and water. And we also fully hydroxylate the aluminum. And once AlOH3 happens, it precipitates out of solution. So does that make sense? Yes, I would never ask you to balance these equations or anything. I think that the take home here is that the bicarbonate tends to scavenge protons. And that's why liming works. Any questions about that? Yeah.
So the bicarbonate scavenger program, yes, that means that those negative sites are then available for different cations.
Yeah, exactly right. And furthermore, by adding enough hydroxyl groups from the bicarbonate, look what's able to hang out on the exchange sites. So that aluminum is getting precipitated out of the solution, which means that we're allowing base cations to persist on the exchange. And then that means that if you knew only that, in this case, what the exchangeable calcium and magnesium were, and in this case, of course, there would be some acid cations. I mean, I shouldn't have nuked all the aluminum because that wouldn't be the case. But if you knew what the acid saturation percentage was in the base saturation, and you knew that the base saturation went up, then you know that the pH absolutely went up as well. Does that make sense?
Yeah.
So there have been some whole watershed experiments trying to evaluate these processes. And probably the best example is Hubbard Brook. Again, this is the long-term ecological research site in New Hampshire that was started by the Forest Service in the late 1960s. And it's still going on today. And they started observing, lots of trends over time. I mean, the commitment to long-term research has been pretty valuable. And one thing that they've noticed is sugar maple decline. And they've also been able to quantify changes in base cation contents in the soil over time. And part of the mysteries of this is ion concentrations are changing in ways that don't really make sense. So acid rain or pollution legislation in recent decades has reduced the amount of nitrous oxides and sulfur oxides that are in the atmosphere. And the pH of our rainwater has actually been going up over the last 3 decades. So how should that have been affecting the pools of acidity in this second growth northern hardwood forest underlain with glacial till in northern New Hampshire? So if we were to measure soil pH now versus 30 years ago, how should the pH or active pool of acidity change, or would they be the same, do you think? It's not a trick question. Should the pH be higher now or lower than it was 30 years ago? Should be higher, right? Because the active acid cations coming into the system have been going down. So what should that mean for the amount of calcium that's on exchange sites now versus 30 years ago? There should be more now, right? But in fact, they're not. So they've actually been measuring declines in exchangeable calcium over time. And we don't know why. So there have been some papers that just came out last year investigating some of the mechanisms that could be at work for this. And they've been doing some experiments where they've been actually adding the calcium back in. So unlike an ag system where you can just have that spreader and drive across the field, this is a northern hardwood forest. So it'd be pretty hard to have a spreader or even have a skidder drive around and try to broadcast the calcium. So they actually did it through helicopters. So they did helicopter dumps of this calcium-rich mineral called wolfstoniite. They basically limed the whole watershed. So it's pretty expensive, pretty extensive, expensive experiment. And just to illustrate some of the changes in forest characteristics that they've been measuring over time. So their experiments are rooted in production forestry. So they do harvest treatments and they investigate the effects of the various harvest treatments on all the things we've been talking about. And here's a time course. And prior to a harvest, you can see that sugar maple represented a significant component of the total basal area. Or for those of you who are engineers, what we're talking about here is if you measured all the diameters of all the trees, you can actually measure the area that their diameters at 4.5 feet occupy. So it's just a way of representing the density. And you can see sugar maple were a dominant component of the stand before harvesting. And then over time, the sugar maple just didn't come back. It never really bounced back. And instead, the yellow birch seemed to take off. And they assumed that this was due in part to coincidental measurements of declines in calcium. Another way to look at components. So here's, again, I know you can't read that from probably anywhere, but the x-axis here is just time. And it's showing, the left graph is showing the sugar maple decline, and the right one is showing a concomitant decline in beech as well. And what these three lines are actually three different positions in the watershed: lower, middle, and upper. So they saw differences in the regeneration, not only over time, but with respect to where they were in the watershed. And this is a table, and I know tables make our eyelids go down, but there's a lot going on in here, so I thought I'd just kind of walk us through it. So here, again, these three tiers are the three parts of the watershed: lower, middle, and upper. And then here's the exchangeable calcium that they measured in both the organic horizons and the surface mineral soil horizons. And what we see here is, centimoles of charge. So these are numbers that we should be getting used to. So this is the unit of measurement. And then they took the exchangeable calcium and they also calculated the percent base saturation. And then they measured the exchangeable cations before and after the harvest treatments. And you can see that the harvesting caused a decline in exchangeable calcium regardless of the landscape position, but it was worse actually near the top or the shoulder slope of the watershed versus the middle or the toe slope. And that checks out because the shoulder slope would be a region of nutrient loss, whereas the toe slope should actually be a region of nutrient accumulation. But in this case, regardless of where you were, the exchangeable calcium was actually going down. Furthermore, there's some other things that I wanted to point out. Notice how the percent base saturation changes with the calcium concentrations. That checks out, right? Base saturation is dramatically higher in the organic layers, which have an order of magnitude more exchangeable calcium than the mineral soils do. What are some of the reasons that could explain that? Why would the centimoles of charge associated with calcium be an order of magnitude higher in the organic layers than in the surface mineral soils? Well, what's an obvious reason right off the bat? What do we know about OA horizon versus A horizon in terms of its CEC? It should be way higher, right? So the organic layer could have CEC in the hundreds of centimoles of charge, whereas a surface mineral soil horizon, especially, these are haploorthods. This is glacially transported parent material, just like we have around here, could be vanishingly small, right? So that makes sense, that the base saturation would scale pretty closely with the exchangeable calcium. So that's good. And it also checks out that we would have a difference in the harvest effect depending on where you are in the landscape. So I just wanted to provide this study. So when we measure CEC next week, it'd be good to have these numbers in comparison with the numbers that you get. So try to think about what sealing and basement values for real cation exchange capacity values measured out in the field, what should look like and how that compares to the values that you get in the lab. So what happened when they added the calcium back to the landscape? Well, they saw a marked increase in the maple. So the maple actually responded pretty nicely to the calcium addition treatments. So it does suggest that that could be one reason why we have sugar maple decline. And we still don't know why the calcium in our soils has been going down, but we do know that when we add it back, it has a nice effect on getting maple regeneration. So I think that's pretty cool that, this is something that we're observing in the forests around here. We don't know the mechanism yet. So if that's an area of interest to you. That field of research is wide open. So it's still kind of an open question. Any thoughts about that or any questions? What are some of the things that might be influencing the availability of calcium in our surface soils? Well, one big change that's happened in recent decades is the proliferation of worms, right? So we're obliterating, 30 years ago, a lot of areas had a nice layer cake of organic horizons that's now getting kind of churned up into the A horizon at a net loss of total carbon. So it could be that nice layer cake of organic material that was so effective at holding calcium, upwards of 8 centimoles of charge per kilogram. If that goes away, that could be having a big effect on the soil's ability to retain calcium. So that's one factor that I think of. You guys think of anything else? And I preface that by saying, I don't know. I think it's cool to think about because it's a problem that we don't have an answer for, but and it's an active field of research. Well, other things that naturally add base cations back into the soil is fire. So after wildfires, there's a short-term alkalizing effect. So the ash elements are typically rich in calcium and magnesium. So you can see a small spike in pH after wildfires. And wildfires also have another effect on cation exchange capacity in that the products of burning charcoal also have really high cation exchange capacities. And that's really cool because charcoal is a potential tool that we have for actually, as a forest amendment, for increasing our cation exchange capacity and our water holding capacity. So a lot of this idea came from observations of soils in the tropics, actually. So have you guys heard of the Amazonian black earths or the terra preta? What is the terra preta? I saw some nods. Yeah, exactly. So the terra preta is an extremely fertile soil in the tropics. So these are ordinarily oxasols. It should be some of the worst soils on the planet. And yet there are civilizations in Amazonia that there were massive civilizations at one time before diseases took them out that had the ability to grow a lot of crops. I mean, to support civilization, you need to have fertile soils. So these are actually man-made soils, and we're really only starting, it's only been about a decade that we've kind of understood how they made them and how they came to be. And I think it's fascinating because if you can improve the soils of the tropics and make them arable, then we should be able to do something about the lousy soils of northern Wisconsin, right? I mean, we should be able to figure out a way to regenerate scrub oak if they could somehow grow crops in the tropics. So we took this same idea, this idea that you can use charcoal to improve a soil to try to get some degree of fertility in our lousy sandy soils. And again, this was all discovered by some work that was done in Amazonia. And I have a short clip that I'd like to show. I won't have time to talk about it today, but I think it'd be fun to look at it on Thursday, describing the discovery of these soils and how they came to be and why we think they're important. Here's one example from a study that just came out less than 10 years ago. Sorry, let's see if I can have if I can move this annoying thing. Yeah, 2006. And these were some soils that they discovered in the tropics. And again, these are those terra preta soils. And what we have here is organic carbon content on the x-axis and cation exchange capacity on the y. And both of these lines we would expect to be positive, right? Because cation exchange capacity should increase with carbon content. That should be a universal truth. But we see very different responses in the line on top versus the line on bottom. So per unit carbon, something's going on with those anthrosols versus these adjacent oxasols. And what's going on there is per unit carbon, the type of carbon that's in the anthrosols is charcoal. So that charcoal has a very different reactivity in the soil than regular old organic carbon does. So that's pretty cool. They were able to increase the cation exchange capacity by a significant amount by incorporating the charcoal. So here's another depiction of that terra preta. So this is, I don't know if you can see it too well, but the tropical soils are these highly leached out yellow earths. And you can see here this dark katina near the top, over 1 meter of this black earth that was man-made over 800 years ago, and it's still there today. So that's pretty amazing in itself, right? In that some of the most highly weathering environments on the planet, we've got these really rich looking soils. I mean, that could be Nebraska, right? Well, why is that hanging out in the tropics? Well, something about the incorporation of charcoal and organic waste has stabilized it in the soil, and it's actually persisted for a long time. So it's interesting that they're still mining this material today. There's another illustration of some of that soil that was amended with biochar hundreds of years ago versus soil that were amended with other components. So even just using manure or other organic waste, there's something special about adding charcoal in combination with organic waste. It helps to stabilize it in the soil. So here, this is phosphate. So this is an anion. So this also illustrates the high anion capacity of the biochar. So it's great for cation exchange capacity, but it also is good at sorbing onto anions. So it's kind of a 1-2 punch for improving soil fertility. It also has a pretty dramatic effect on the water holding capacity of the soil. The charcoal is loaded with surface area, but it's less dense than clay is. So it's even more effective at holding on to nutrients in water than adding even an expansive clay would be. So here are some planting trials in Colombia where we've been trying to experiment with, well, if these ancient Amazonians could create this stuff, how can we recreate it? Can we find what the magic recipe was for combining charcoal and organic waste to make a really fertile soil? So they've been doing a lot of field trials with this. And more recently, we have started using this in forestry. So some work that's been led out of the University of Idaho in particular has been experimenting with adding biochar, primarily in plantation forestry, but we've started doing it in other applications as well. So the reason why we think it works is because it's just got a super high surface area. So that makes sense. I mean, charcoal is what they use in masks and filtration devices. It's because they just loaded with surface area. So it improves the CEC, has a high surface area. It also has a biological component. So in the movie that we're going to watch on Thursday, they talk about how it's not likely just a physical process, but something about the interaction between the organic material and the high surface area provides a refuge for unique consortia of bacteria and fungi. And it's those consortia of bacteria and fungi that in some way, which we don't really understand, increases the mineralization capacity of the soil. So it's just a great combination of factors. And then of course, charcoal can last in the soil for hundreds of years. So that's another, so it's this organic amendment that is persistent and reactive. So biochar is made in high heat at the exclusion of oxygen. We do not have any facilities that I'm aware of in the Lake States for buying it commercially. When we did it for our field trials, we had to buy it from out west. So that is one thing that makes it cost prohibitive around here. I have been making it myself in a highly sophisticated process called a burn barrel. And we've been using it, that homemade biochar, for a lot of our experiments here in the Lake States. So there's been a lot of buzz about using biochar to increase carbon storage. And the idea being that you've got this organic material, that's made from photosynthesis. And if you can somehow have it through this activity, if you can somehow convert this organic material into something that's persistent and build soil, it should in some way be able to greater accumulate the amount of carbon in an ecosystem. At least that's the idea. So this idea was pitched in 2007, and it actually got published in the journal Nature. So this was a big deal when this idea came out. So what they proposed, and I'd like to hear your opinion on this. So this is a normal ecosystem. Generally speaking, most ecosystems they're approximately at equal balance with respect to how much carbon they take in versus how much carbon they release, right? I mean, there are very few ecosystems that are just massive storehouses of carbon, right? Where the inputs just dramatically exceed the outputs. That's why when we walk in a forest, we're not up to our eyeballs in detritus, right? There's not very much accumulated organic matter. So roughly speaking, net primary production approximately equals the amount of carbon being respired out, plus or minus a very small residual. I mean, if you don't disturb a forest, that's why old growth forests harbor a little bit more carbon than rotation forests do. It's because over time, you do have very small residual that accumulates, but generally speaking, it's pretty hard to accumulate lots of carbon. But what Johannes Lehmann, professor at Cornell, proposed is that if you intercept the detritus inputs that normally would come into the soil, if you intercept them and convert them into biochar, that should fundamentally alter their residence time in the ecosystem. And there would be a feedback where this black carbon or charcoal helps to build soil faster than it otherwise would. So he proposed that detritus that undergoes pyrolysis or gets converted to black carbon would be more persistent, and it would help to build more soil, releasing less carbon dioxide to the atmosphere. So what do you think about that? Does that seem like snake oil? So yeah, let's think about some of the feasible aspects. So what are some of the big caveats here? Like there should be an asterisk here that's almost bigger than the graph, like huge asterisk. What are some of the considerations here? Well, I'd like to know what the life cycle is of that pyrolysis itself. So let's just take a look at this thing. Do you think that some carbon was released in making this black carbon? Yeah. Maybe a bit, right? What other things? Sorry, I didn't mean to cut you off.
The feasibility of getting that much of a layer of biochar over in there.
Yeah, so okay, here's this factory representation of a pyrolyzer. all right, so somehow we got the slash material to here. And now we've got to somehow get it back out into the woods, right? So what's the energy cost associated with that? I don't know, but it's not going to be easy. So there's a lot that's not considered in this equation. But in theory, it's an interesting thought, right? That you could actually convert this biomass. So what are some things that might make this feasible? Like, I don't want to be a total downer. Like, yeah, what do you think? Exactly. Like maybe if we could bring the pyrolysis unit to the site, maybe that would be starting to get us closer to making this feasible, actually. Or maybe we could make the black carbon actually on the ground with using lower tech methods. And that's something that we've been experimenting with. So actually, combining the slash material and covering it with soil. So set it on fire and then smother it. So that would be the exclusion of oxygen component. And that's actually how, so the Pavlis Institute has some students go to Ghana to do exactly that. And it was actually pretty successful. So we're getting closer, right? There are some things that we might consider. Maybe if we can do some low tech methods for converting biomass to charcoal on site. And then there's still some energetic costs about trying to actually incorporate it into the soil, trying to broadcast it. But we're getting closer. Like there might be some ways, some methods that could get at that. What's another factor that's important in this that's not being represented is, what do you think happens if you add, so we said that black carbon, and you saw those microscope slides of the cross section loaded with all that surface area, just smoking high cation exchange capacity, smoking high anion exchange capacity. Let's say you took that right out of the kiln. How many exchangeable nutrients are associated with that black carbon? So it just came out of an oven that was 500 degrees for 8 hours at the partial exclusion of oxygen. It's not loaded, right? It's like an empty battery. So what little science has been done, and we'll be able to talk about this a little bit more on Thursday, is that they found that if you put a bunch of charcoal that has not been mixed with organic waste into the soil, it actually imposes a nutrient depression, wherein it ties up. In other words, the CEC of that charcoal is so high that it makes it harder for the plant roots to compete for actually taking up those nutrients. So it could have a negative effect, in adding basically dead battery into your soil. Something we're going to talk about in 2 weeks is some of the factors that determine decomposition of these substrates or making the nutrients available for plants are all determined by the ratio of carbon to that element. So in particular, the ratio of carbon and nitrogen. If you add a whole bunch of carbon into the soil, it's going to be very hard for microorganisms to attack that material and release the mineral components. So these are all some things that could work against us in trying to actually carry this out on the landscape. Any other thoughts about this? Anything else that you'd want to bring up if you were reviewing this paper for Nature before it got published? I think those are the big caveats, though, are just the energetic constraints of actually making the stuff, getting it out on the field. If we could work out some of those bugs and figure out a way to charge the battery before we include it in the soil, I think that this could be a good management option in some situations. Any thoughts about that? This might be a good place to stop before we dive into some of the case studies. I did put a very short case study on Canvas. It'd be good if you could read it before Thursday. Make it more interesting for me anyways, if you could have a conversation about it. Any other questions? All right, thanks. Have a good afternoon.